In the previous section, we learned how to make physical settings with graphs. Now you're going to see how paths and circuits can solve problems such as constructing efficient routes along city streets for garbage pickup or mail delivery. We've seen that a path in a graph is a sequence of adjacent vertices and the edges connecting them. Recall that an edge can be a part of a path only once. If a path passes through each edge of a graph exactly one time, it's called an Euler path. So let's go ahead and create an Euler path, and we're going to go ahead and start from vertex A, and then we're going to end at vertex G. All right, so going from A, I only have one option of where I can go. I'm going to go ahead and label that 1. And from here, I've got all kinds of directions I could go. I'm going to go ahead and head over to C. That'll be 2. From here, I have to take E. That would be 3. I could go back down to F. So that would be 4. Up to D. That would be 5. And then I'm going to have to swing this, well, I could swing up too. There's multiple ways to draw these. So I'm just picking one that, remember, you do not want to repeat any edge. That's part of the definition of a path. So this will be 8. And then I have my last one to get to G. That would be 9. Okay, so there's my path starting from vertex A to vertex G. If you have a hard time following along, pause the video and go ahead and get it written down. Then, if an Euler path begins and ends at the same vertex, it's called an Euler circuit. Let's find an Euler circuit starting and ending at vertex A. Well, I'm going to go through the same process here. I'm going to start at A and go to B. So that's path 1. I can do anything I want. Let's see here. I think I'll go to E. That would be 2. Then I'm going to choose to go up here. And that's going to be 3. I can go through the same vertex multiple times. I just can't hit the same edge multiple times. Let's see here. That was 4. So now I'm going to go down here and do 5. And then I think I'll come across here and make that 6. Come down here. That would be 7. Up this way. And again, if I'm going too fast, just pause the video after each line that I make if you want to follow the same one. And then this one. Okay, and again, there's multiple ways to do it, but that's just one of creating a Euler circuit. Okay, a couple things to remember is that every Euler circuit is an Euler path. However, not every Euler path is a Euler circuit. So same thing with our paths and circuits that we had before. Some graphs have no Euler paths. Other graphs have several Euler's paths. Furthermore, some graphs with Euler's paths have no Euler circuits, and Euler's theorem is used to determine if it contains a path, a circuit, or neither. So let's take a look at these and kind of interpret them into shorthand that we can understand. If a graph has exactly 2 odd vertices, then it has at least one Euler path, but no Euler circuit. Each Euler path must start at one of the odd vertices and end at the other one. Now, real quickly, remember when we had vertices, right? So I'm going to put 4 examples here. If I have one edge coming out of it, that's going to be an odd vertex. If I have 2 edges coming out of it, that would be an even vertex. If I have 3 coming out of it, that would be odd. And I could have 4 coming out of it, and that would be even. Okay, So just keep in mind that you have our odd and even vertices. Okay, so we know that an Euler path has exactly two odd vertices. And the other piece is that we must start on one of them, on one odd, and end at the other odd. Okay, so that's a path. Let's take a look at our circuit. If a graph has no odd vertices, meaning that all even vertices, it has at least one Euler circuit, which by definition is also an Euler path. So an Euler circuit can start and end at any vertex. So let's go ahead and write that down. An Euler's circuit all even vertices start anywhere. And we're going to come back to these. And then if the graph has more than two odd vertices, then it has no Euler path and no Euler circuit. So neither greater than two odd vertices has neither path or circuit. And this is important because once we start looking at some of these diagrams, you don't want to start drawing and putting time into it if you end up with something that just can't be drawn, okay? So that's part of what our strategy is to get this done.